Hello everyone. Welcome people also join and then we will get started again. Okay, so let's get started. And so first we will have a small quiz regarding the topics that we have covered so far. So I will be. It is only regarding the buffer overflow exploit and stack canaries or WXOR and ASLR, which we have looked at briefly. And so let us look at these problems and let's try to answer them. So I will be copying pasting the question. I've already done the first problem, copied and pasted it in the Q&A, and you can try to answer this. So the question is, what specific memory regions that does a stack buffer overflow target, and why is it vulnerable in software applications? There are four options. The first is the heap, second is the stack, then the data segment, that the code segments, and then you have the reasons due to its dynamic allocation nature for heap, due to the fixed size buffer storage of local variables. In the stack, due to the read-write nature of the data segment, and due to the execution permissions in the code segment. You can also go to the Q&A and add here, but the chat is also fine. Uh, Yeah, so it was definitely easy. It's a stack buffer overflow and it's is targeting the stack. And we, as we have already seen, it is because the sizes that we are allocating, they are fixed in size, and that's the assumption. And if you and the local variables of the programs are stored on the stack, and if you overrun the stack buffer, then you can corrupt the local variables stored on the stack. If there is any another answer, then you can let me know. Otherwise, let's look at the sorry for mistake. Let's look at the next problem here, which is in a stack buffer overflow attack, what specific data on the stack is typically overwritten by the attacker? Local variables, function, function parameters, return address, stack pointer. So which specific data on the stack is typically overwritten? Yeah. So this is it, as we have talked about this very extensively in the last hours, that the return address here uh, in, is like it's very important to protect the integrity of the return address. And of course, other things like local variables and the function parameters are also very important, because they by changing the local variable function parameters, also you can modify the program output or the program flow. But here, of course, typically what we want to prevent by from the attacker is the return address. Yeah. So then the next one is, how does an attacker typically inject malicious code into a vulnerable program during a buffer overflow exploit? Option A is by overwriting the return address with the pointer to the injected code. Second is by appending the malicious code to the end of the buffer. Third is by modifying the function parameters to execute the injected code. And the last option is by manipulating the heap to allocate memory for the injected code. Yeah, so that is right. So option A is right here. So attacker to so as we have seen when we were looking at the shell code example, so there in the vulnerable program, the attacker is going to write the code in the buffer, and then the attacker is going to change the like basically is going to create a payload. The payload is first going to write the code onto the buffer and then change the return address so that the return address points to the injected code. Next one is, how does a stack canary work and what role does it play in detecting buffer overflows during program execution? First option is it adds random data to the stack before the return address, and upon a function exit checks if the canary value has been modified. B is it encrypts the entire stack, making it unreadable to stack attackers. C is it prevents the execution of code on the stack, thus mitigating buffer overflow attacks. And D is it dynamically allocates additional memory for stack buffers. So this is also right. It's option A. So we saw that in the stack canary, the compiler is going to add a stack canary, which is basically a random data value that it keeps a copy of before the return address. And if the buffer overflow attack happens and if the stack canary is overwritten, then at the function exit, when the canary is checked against its original value, when basically the integrity of canary is checked, then it will be caught and the stack attack a smashing attack will be detected. Now the question is, what happens if the stack canary value is found to be altered during program execution? First is the program crashes with a segmentation fault. Second is an exception is raised and the program execution is terminated. Third is the stack canary value is reset to its original value. And the fourth is program continues execution with no action taken. Yes, that's it. So uh, when the canary value is found to be changed, then that causes an exception in the program, and then the control is passed to the exception handler, and the exception handler is going to then terminate the program, and the user will be like, you will get a message on your terminal saying that the stack smashing detected. So it will lead to a exception. Which of the following memory regions does ASLR randomize to prevent exploitation of software vulnerabilities? Stack, heap, libraries, all of the above. Okay, so the right answer here is actually all of above. And although we looked at only the stack in example, but ASLR randomizes all the components, all the segments of the program, including the stack, heap, libraries, even the text segment, which is containing your code. And it does so because when you are rewriting, say, the return address, so you not always have your attack payload only in the that sometimes you are like say like for example when we were looking at that foo bar example, right, so at that time we had modified the return address such that it points to the next skips the next instruction. So the attacker can sometimes like not always is trying to change the return address to point to some value on the stack itself, but sometimes they may want to say subvert the control flow of the program to some other locations, like maybe tries to call a library function to execute a system call, like we saw in the case of this invoking a shell. There we were making a system call, and so we will have to specify the address of the system call or the address of this string slash bin slash sx and so on. So not only the stack, but also other components, including heap, libraries, text, a segment, etc. So all of them are randomized with ASLR. Okay, so the next one is, how does ASLR affect the predictability of memory addresses in a process's address space? A, it makes memory addresses static and predictable. B, it randomizes the memory addresses with each process launch. C, it reduces the address space of the process. And it eliminates the need for memory address translation. Yeah, so the answer is all of you have got it right. B is the right answer. It randomizes the memory addresses, but the main thing to focus here is with each process launch. So if you run your process once, then you terminate the process. If you run it again, then every time the process address space will be randomized with a different layout, like it will be randomized completely differently. It so this say if your main function was located at address X, in the first invocation, it could be located at some other address the next time. So it is randomized with every process launch. Next, and I think the last problem is regarding the W XOR X security principle. And the question is, what does it enforce regarding the memory pages? Yeah, so A is right. So it enforces that the memory pages belonging to the say code segment, they are only executable and not writable. So any page, memory page, if it is executable, then it should not be writable. And any memory page, if it is writable, then it should not be executable. Like it cannot be executable. So the permission of the pages are such that the page can either be writable or executable, but not both. So with that, after this, now I think all of you got like men or most of the answers correct only. So that means that all of you have understood the stack buffer overflow, vulnerability, and got an idea of this, the vulnerability, the attack, and also the defenses. Now, I have put the demos actually in the GitHub repository, and I have copied the link to that on the chat box. And you can then copy that, you can clone that GitHub repository, and I will put it back. So you can then clone this and you can then try the demos. So now I will, so now we will look at the demo. But before I go to the demo, if you have any questions, then you can leave them in the chat box and I can look at them now. And if there is none, then I will start with the demos. Okay. So we will have these four demos. I have these four demos planned for today. And the first one is using GDB. So GDB is a debugger, and it's basically a tool by which you can, with which you can run your program and then you inspect the working of your program. You can look at the binary. You can basically you can look at the assembly code. You can look at the stack, or you can inspect the value of the registers, etc. So we are going to look at the. We are going to compile a code, and then we are going to run it with GDB, and then we are going to look at the various commands. Basically, it's of course not complete list of things that you can do with the GDB. It's very extensive, so I encourage anyone who is interested, they can go and find out more commands and more things that you can do with GDB. But what I'm going to show here in this demo is how you can use GDB to inspect the content of the stack, the registers, how you can see where your program is currently like which instruction is being executed or will be executing next, and so on. And this will help you in the next demos, because we have to look at the stack in order to be able to do these buffer overflow exploits. So with that, here first we have this very simple test.c program, which is similar to what we have had in the slides. So here we have two functions, main and foo, and the main function is calling foo. There I had more arguments, like three arguments. Here instead of three, I have only two arguments. One and two are being passed to foo, and then the foo uh, is of course taking here two integer arguments, and then it is creating two buffers, buffer one and then the buffer second buffer here, and the buffer one is of 5 bytes and the second one is of 10 bytes. So then we are going to compile this program, and then we are going to run this program. And so basically, there is no print statement also in this program. It got compiled and you can run this. Okay. And so yeah, so this is the text file which contains the different commands that you can use. Like you may need, like later you can look at them, and we are going to use these commands now when we are running with the GDP. So first we are going to compile, right? We already did, but when we are compiling the program, then we can specify some flags. So here in this me yeah, so in this command here we have this command here, the first flag here is -f no stack protector. So this is related to the stack canary basically. So what we are saying is we are telling the compiler to not use stack canaries here. Then -z exec stack. So it is again because we want to first do these attacks. So we have to disable the defenses, right? So then this one is to enable the stack and make it executable. And then we have no PIE, which is program can be say program in like it can be like say basically it should not be say relocatable or like what was that? I forgot. Like basically it should not be say relocatable, or it has to be say it is always the layout is same of other. And here the -g flag is for the GDP that we want to compile this program with the debugging information that then GDP can use. Okay, so and -m is to create a binary for 32-bit systems. That is like just a flag. And why we are doing this is so that our binary looks more, say, uh, like it will be easier to understand it. Okay. So when we run this command, then we are going to create this test -o. We have specified the -o option here is that we can give the name to the executable. So the test executable is created, and then we can run it with GDB with gdb./test, and then we are running the GDB here. And so first of all, we what we can do is that we can just use the list command to list the program. Okay, so here this is the program, and these are the line numbers for each line. And so the first so currently the program is actually not running. Okay. Now to run this program, you can give the command to GDB R. And if there are any arguments to the program, if the program takes any argument, then you have to specify the arguments. Here there are no arguments, so you will run it, and then it will run where it is running completely and it exited normally. Okay. Now, because we want to inspect this program, so we may want to stop this program at some say locations. So for that, GDB provides something called breakpoints. So you can add breakpoints, and a breakpoint basically lets you stop the execution of the program at that line. So you can say break the execution at line number 7. So this B is for adding breakpoints. 7 is the line number, and when you will execute it, then it has added a breakpoint. Instead of the line number, you can also give an address. Also, from if for that you will have to look at the addresses. Now you have added a breakpoint. So if you want to now run the program, so you can again use R. And when you use the R command, like when you give the R command here, then the program will execute, but it will stop at line number 7. Now, it has shown here that it is here. Now, if you want to see that where it is exactly, so you can use the disassemble, and then the disassemble assembler, like you can use the obj dump command utility to or obj dump tool also to like get assembly code of the to disassemble the binary to get the assembly code. But inside the GDB also you can use disassemble to get a dump of the assembler code for the function. And here currently it's showing for the function main, because currently the instructions are executing from function main. Okay, so here, but in addition, here it also shows a pointer, which is here, the arrow, which is pointing to the instruction, which is going to be like executed. Okay, so it is showing here that these instructions have executed, and currently the instruction pointer is here. Now the instruction pointer, and in our function main here, we have a call to foo, which you can see here that main is calling foo, there is a call instruction, and we are passing these two arguments 1 and 2, and then we have these two instructions push 2 and push 1. Okay, and I mean we had looked at this earlier, that after that call will be returned, then there is this is happening now not for foo, because for that code will be there in the foo, but this is the cleanup code for the main function when the main will return. Now let us look at first say the stack. So for that actually what we can use is that we can print the first let's look at the register value, register contents. So you can use info registers to inspect the value of the registers. So here, let's look at first the EIP register, which is the instruction pointer. And as you can see here, it is the value 0x8048412, which is same as here. This is the instruction pointer. Right? You can also use to get the register values of ESP and EBP. So ESP is your stack pointer, EBP is the frame pointer, which we had seen in the slides. And currently your stack pointer and frame pointer are both pointing to the same location on the stack, which is this FFFFD3A8. Okay, and why is it so? Because when you entered in the main, there is this code first to push the value of EPP, then to set the value of EBP equal to ESP. Okay, so that's why they are same, but after that, the value of ESP has not been changed anywhere because there are no local variables or anything in the main function. So they are same and they are pointing here. Now, okay, before I move forward, let me look at the chat and see if there are any questions. Hmm. Okay, so now next, to inspect the stack, what we are going to like, what we can use it, we can use x/32x, and then the address of the stack pointer. So you will use this command here. X is for printing the values, and then the 32x here is basically specifying that print 32 locations in hexadecimal, and like 32 values in hexadecimal notation, and starting from the address specified in the ESP. So when we do this, then this is what we are getting. Okay. Now, so now let's look at it here. And so this is currently where you are, okay, in the instruction stream. And this is how your stack frame is. Now the next instruction is what? A push 2, then push 1. So what do you think will happen if the next instruction is going to change? Sorry, going to get executed. So here, the value of ESP is this value. So can you tell me, you can write your answers in the chat box, if the value of ESP is FFFFD3A8, if we execute the next instruction, push 2, then what will be the value of ESP? How will the stack content change here? Why are both the pointers together? Yeah, so I will explain again. 4 bytes plus 4 bytes stack will have 2 at ESP plus 4 bytes. Okay, first of all, I will answer the question which was asked, why are both the values equal? Uh, so I'm assuming that you're saying why both the value of ESP and EBP are equal. And I'm not sure if that's the question, but I'm assuming it. If not, then please correct me. So values of ESP and EBP here are equal because we have just started executing the main function, okay? And in the main function, the first instruction is to push the value of EBP. So the first two instruction here, they are forming the function prologue. So that is setting up the stack frame. So they're setting up the stack frame for main function. So first instruction is push EBP, and then the second one is move the value of ESP to EBP. So let me just look at the slides here. I am not sure what's the problem with these slides. I think it will be good for me to once again just go at the slide where we had looked at it. Otherwise, I will have to draw something. So it's better that I do it here. Look at it here. Yeah, so when we were looking at this, uh, so this is what is happening for foo, but the same will happen for actually every function. So consider that your EBP is currently pointing here, which is the start of the stack frame of the main function. Okay, and your main function has say like this code is actually same, right? So there is nothing initially there in your stack frame. because main here has no local variables. But after that, you're calling foo, so you have pushing these arguments there, 3, 2, 1. Again, I have so just I want to emphasize on the fact that the stack grows downwards. Okay, the stack grows downwards. So if the stack address here, initially stack was here, which was equal to EBP when the stack frame of main was started. But every time you write something on the stack, it will grow downwards. Okay, so then it will decrease basically. So when you are writing like here, basically, initially your ESP is here. When you push value 3, it goes down by 4 bytes. When you push value 2, it again goes down by 4 bytes. When you push value 1, it again goes down by 4 bytes. And then after that, you're going to push the return address, okay, which is done by the call instruction. And then the value of EBP, that is the start of the previous stack frame, is pushed, and then the value of EBP and ESP, then the value of EBP is changed and it is set equal to ESP. So this is the process of function calling. You first are going to push the arguments in reverse order. You push the return address, then you push the value of the EBP, which is the uh, stack frame address of this main function, which is calling foo. Then you set the value of EBP equal to ESP. So this is what we are inspecting basically now with this example here. And that's why the value of these two are same here. Now the question that I have asked is that currently my instruction pointer is here. That is, this instruction will get executed next. And this is how your stack content is. Like this is how your stack looks right now. Okay. So your stack pointer is D3A8. Like it is the location which is here, FFFFD3A8. And the value which is stored at this address is this. It is 4 bytes. Okay, 4 bytes. So that means not at this address. Of course, addresses are, you will increment them, say byte by byte, but 4 bytes are stored here. That means this address here is actually D3A4. Okay, so this is D3. This is the content of the address D3A4. And this is the content of the address D3A0. Right, so this is how your stack is. Currently, your stack pointer is here. So this is basically what your top of the stack contains. It's all zeros. And you're currently in the main function. Now, the question is, when this push instruction is executed here, how will the content of your stack change? What will be the value of your ESP? That's the question. So let me look at again in the chat box and see if there are any answer. I hope that I was able to answer your question. You and so the answers that you have given me so far, that the addresses will increase by +4, actually that is not right. So I would so if you can look at it again and like see with what I just told you, that the stack grows downwards. Okay, and so when you're going to push the value to, how will the content change? How will the value of ESP change? So let's just do it and see. So then the GDB has this command SI, which stands for single instruction. So when you give this command SI, so what will happen, that only one instruction will get executed. So when you do SI, then one instruction will get executed. And now let us disassemble and see whether it, yeah. So now the instruction pointer has moved downwards. That means the push to instruction has executed, right? So now let's look at the value of these registers from previous. Earlier, the value of ESP was D3A8. Now the value of ESP is D3A4. Okay, yeah. Actually, I've made a mistake here. So when I was explaining to you here the stack addresses, so they are actually higher addresses and not lower. So this will be like, yeah, so this is DA8, then this is DA8 plus 4, and this is DA8 plus 8 in hexadecimal. So they are actually increasing by 4 bytes from year to year. I'm sorry for that. Yeah. Now your stack is like will be growing downwards. So that's why your ESP value is decremented by 4 to push value 2 on the stack. So look at the stack content. That is, we are going to starting at this address. What is this address? We are currently here printing starting from the top of the stack. So this is the top of the stack, and the top of the stack contains value 2 which we have pushed, and here we are printing like 32 values from the stack in hexadecimal format. Okay, is that clear? Yeah, so that's right. It will be decremented by 4. And now again, now the next instruction is push value 1. Can you now tell me what will be the next value of ESP and what will be the top of, what will the value on the top of the stack? So I've asked the question that if the instruction pointer is here, so next you are going to push value 1 on the stack. So when this instruction gets executed, then what will be the value of ESP? Current value of ESP is this, ending in A4. And what will be the value of, so here I will ask you value of ESP, EBP, and what will be the top of stack. So you can answer all of them. And let me just copy the current value of ESP. Current ESP is this. Uh, yeah, ESP will be A0, EBP will be same. Yeah, so that is right. So ESP will be decremented by 4 bytes. So it will become FFFD3A0. EBP is, there is no effect on EBP. It will remain the same. In fact, it will remain the same throughout the execution of the, it is always changed only once when you are just like in the function prologue or in the function epilogue, only change at that time. Otherwise, it remains the same. And you're going to push the value 1. So let's look at that. So, sorry, I have not actually run this instruction. We run this instruction, then we are going to look at the content. So now, and then let's look at the info registers. So here the register ESP has been decremented by 4 bytes. It becomes A0. EBP is same, and the top of the stack now contains value 1. So this is okay. Now let's look at next instruction is call instruction. Okay. And this is a call to 80483F2, which is the address of the foo function here. And this is the, so now first tell me what is the address of call instruction? Let me just copy. So this I will just copy for your, so that it's easy for guys, but it's copied correctly or not? It's I think. So can you tell me what is the address of the call instruction? Yeah, so that's right. The call instruction is here and the address of the call instruction is this value 8048416. So, and what happens when we have this call instruction? What happens when the call instruction is executed? So the call instruction when it executed, it not only alters the program control flow, it not only change the program counter and like the basically the instruction pointer to start executing the function foo, it also pushes the return address on the stack. So what will be pushed on the stack as return address here? Yeah, but what is the address? Okay, yeah. So actually, the address of the call instruction is this. Now, when you have called the foo function and when you return, where do you want to start from? If you say 8048416, and I don't know what was that. So if you say 8048416, that means you're saying, okay, when you return from foo, then run the instruction located at 8048416, which is again the call to foo. But that's not what we want. We want to, because what we have already executed the call to foo. So next we want to execute is the next instruction, which is 8048441B. So we are going to push this value on the stack as return address. Okay, so then let us execute the next instruction. And let's see first what happens. So here, if you will see disassemble, if we do, then actually we have now see the disassembly of the foo function because we have entered in the foo because we executed a call instruction. And if you see here, then we had here 80483F2, which is actually the address of the foo function, the first instruction in the foo function. And the instruction pointer is currently pointing here means it will execute this instruction next. So this is the EIP. Now, what is going to be, so I just said that this is the return address. So let's see if this return address has been pushed onto the stack or not. So let's for that have the, this is what we do to print the content on the top of the stack, right? So the call instruction only did two things. One is it like changed the instruction pointer to this address here. And second, it not here, sorry, to this address here. And second, it added the return address, which is the address of the next instruction onto the stack. And this address here, 8048441B, is actually now on the top of the stack, as you can see. And if you will look at the next bytes, then the next byte is 1, and then sorry, not byte, the next 4 bytes are 1, and the next is 2, which are the function arguments which have been pushed onto the stack. So with this, you have like basically pushed the arguments on the stack and you've pushed the return address. Next, what happens? So we saw that next when this function foo is going to start, then the first instruction here is push EBP. So it is going to push the content of EBP on the stack. So what is the content of EBP? Yeah, so the content of EBP is FFFD3A8, or if you recall, then actually this is same. When we had first started the program, this was this only. So this is pointing to the stack frame of the main function. So, but we have now we have to execute the foo function. So we are going to store the stack frame starting address of main on the stack now, so that we can restore it later. And so if we do the next instruction, we are going to execute, and then we look at the stack frame, then we will see that this EBP value of EBP has been pushed onto the stack. This is the value of EBP. This is the value of, return address. These are the arguments. This is exactly what we had seen in the slides, right? Next, we are currently the value of ESP is this 3, FFF93T9, T398. This is the current value of ESP. So now we have to set the value of EBP equal to the ESP, which is done by the next instruction. So if we will execute one more instruction, and then if we will look at the, okay, now here we have executed this instruction. Okay. Can you tell me what will be the value of ESP and what will be the value of EBP? This is your stack. This was your stack before I executed this instruction. So before this instruction was executed, this was the stack. This is how the stack looked. This was the EBP value. Now, what will be the value of ESP and EBP? Yeah, that is exactly right. But what is the value? Is it FFFD398 or is it FFFD394? Or like, what is that value? Yeah, so that is right. It is D398 because the stack is not changed. Like you're not decrementing the stack pointer. Whatever is the stack pointer right now, which is this, the top of the stack, it's just getting copied here. So your info registers, ESP, EBP, they will be same. Okay, so that's what we have seen now. Well, the next instruction actually, let's look at first disassemble. Yeah, the next instruction is subtract 0x10 from ESP. Now, what is it doing? So if you list your program here, this is your program. The program has these two character buffers. Buffer 1, 5 bytes, buffer 2, 10 bytes. And now what is this line doing here? So this line here is actually allocating the space for your buffers. Okay. And it is here allocating 16 bytes of space, right? It is allocating 16 bytes of space for these two buffers. Although the buffer are 15 bytes, it's allocating 16 bytes. And so that is actually sometimes because of alignment. The compiler wants to say to relative addressing. And so that's why sometimes it will align, it may allocate more bytes than what the size of the buffer is for some optimization, etc. And so then the 16 bytes are allocated. Now, if we inspect the stack, now how it will look like. For that, let's look at the, first of all, here, the value of registers. Okay. So note that I've actually not executed this instruction so far. Okay, so I'm just showing you that this instruction is going to execute, and it's going to subtract value of ESP by 16 bytes here. So now if I execute this instruction, then the value of ESP should be changed by 16 bytes. So it has changed by 16 bytes. And now if we look at the content of the stack, then this will be this. So take a moment here to see what, like, if you can like look at it and see if you understand or the layout of the stack. And if you have any question, if something is not, you don't understand anything, then please put your question in the chat box. Yeah, that is right. And okay, so there is no question. And the 4 bytes were allocated, and these are the 4 bytes that were allocated for the buffers. And this is your previous stack frames frame pointer. Uh, I mean, this is the frame pointer for the main function. This is the return address in the main function. These are the arguments for the full function. Okay, so after this here, in the foo, basically you're not doing anything, right? So then you will just now return. And then there is some additional actually here call to some other function get PC thunk. So this is related to computing the program counter value and next instruction also. So after that, uh, we have these leave and read instructions. So let us just now what we want, let's just skip these instructions, okay, the call add etc. So how can we skip these instructions? So for that we can add a breakpoint. So how can we add a breakpoint? That we can do break, and then we can add say the address of this instruction. Okay, so if you will use B with star and then the address, then you will add a breakpoint at this address. Now, if you continue the execution, you will have executed these instructions, and now the instruction pointer will be at leave. So now let's look at it. So now here we are. Now but the content of the stack frame actually, uh, I mean, the content of the stack should not be changed because we have not pushed anything on the stack or anything else. So this is same as before. Now, when the leave instruction will execute at that time, you're going to, so there are two, leave and read. I'm not very sure how they are dividing the work within themselves, like setting up the EBP or like red definitely reads the return address from the stack. So now let's look at that. First execute leave, then we'll see how the stack has changed, and then we will execute red and then see how the stack has changed. So first we execute the so first we are having going to execute one instruction, leave instruction. Now let's look at the stack. So what happened here? 39C. Okay. So it has, okay. So here what it has done is it has removed actually everything from here. Like it has removed the like not removed anything, basically it has changed the stack pointer. So the stack pointer has been changed here, and it has been incremented, and the frame pointer value, previous frame pointer value which was stored here, that is restored. Okay, so let's see what is the value of the frame pointer now. Yeah, so that value has been restored. Now your EBP contains the value which was stored on the stack. This. So the leave instruction has restored the value of the EBP. And now the top of your stack contains the return address, which will be read, which will be popped up basically by the return instruction, ret instruction. And then the ret instruction is going to return back. And then this final, this all of these this will be handled by the that side, I think, main function. So then let's execute the next instruction, and let's look at the content of the registers. The content of the registers is now here. EBP is here. ESP is 3A0. 3A0. This is AC. This will be A840. So I think you are basically here now in the stack frame. So it has only popped up the address, return address. Yeah, so the red instruction only popped the return address. And now it has actually returned back to the main, because when we executed it, then we got this that we have, sorry, we have returned back here. Okay. And this is the top of the stack. I mean, basically, this is the stack. This is the top of the stack here, and the frame pointer has been restored. Now let's look at the let's disassemble this and see. So now we have returned back to the main, and the instruction pointer is here. So now, uh, what is this doing? What do you think this instruction is doing here? Add 8 to ESP. Okay, I've noticed that the array values by default are 0 on Linux and garbage values when compiled with this on Windows. Here, maybe due to something in the options. So that might depend on the compiler. Uh, Here, the buffers are actually, as we saw there, the stack contains any garbage value. Yeah, so that is right. Here we are, this instruction add 8 ESP. This is popping up so basically changing the ESP. And by 8 bytes, so that now these two values are no longer existing. Like now your ESP will point here, and you have effectively popped up the parameters that you had earlier pushed onto the stack. So now let's execute this and get the content. This is how your stack was when you had to first like call the foo function. So now how will the main return? So for the main function also, we will have the values of EBP and ESP, EBP value. So where will the main return? So it will return to the runtime, C runtime, so which started the main function, and the return address is also stored in the stack. We are on the leaf. Okay. So the EBP here is all like 000 because there is no function before this. I think so that's why it's all set to 0. And then this must be the return address, which will execute, which will return back. And then currently, I think we are on the red. And when we will execute that, then it will actually return back to the libc start main. Okay. So it is returning back to the library, which had called the main function to start. It's located in the libc. So that's the so we have looked, that's how with the GDB, how you can inspect the content of the stack and how you can execute instructions one by one and do it, right? So I'll continue and the execute. So now if you have any questions about that, what we saw in the demo now, then you can please ask. Otherwise, what I will do is that I have posted the GitHub. Please clone it and just compile the file, try to run GDB. You have the list of the commands here with you, right? Cat commands. Ext. and just try these commands. I mean, you don't have to do whatever I did completely. Uh, don't have to do whatever I did or all of those steps, but just do it and get yourself familiar with these commands. And if you have any questions, then you can ask the questions. So I will come back in like 5 minutes, but the meeting is going on. And meanwhile, you can try that will give you some time to just try it. And if you get questions, then you can ask. And after this, we are going to then continue with the next demo. Okay. Hi everyone, I'm back. And so I see some questions. Okay, so the first one is there are so many registers there. How do you differentiate one from other? Okay, I don't know which registers you're talking about. So if you can specify, that would be good. Okay. Yeah, so as you have already got an answer. Yeah, currently we are only focusing on these two, three registers because currently we're only analyzing the start and end of the stack. And yeah, okay. Getting error in compiling with first marks. What is the error that you are getting? So it is possible that you may not have the lib32 in your system. So for that you can install that library. I think I have edit it. Were you able to resolve the error that you're getting in compiling? Okay, for those of you who are have been, let's say, if you're able to compile and if you're able to run it with GDB, then please let me know in the chat so that I know that it's working and how much more time we need for this. Okay, thanks. So when you guys have are let's say done with running GDB and trying these different commands, then please write in the chat box that you are done. And then we will move on to the next uh, demo. Okay. Yeah, for now you can use the pre-compiled version and then you can debug the compilation errors later. So hi everyone. I hope that you're able to do the demo. Those of you who have finished, you can write that in your chat box that you're done. And then if you are not able to, if you're getting any errors, then you can let me know. Put it on the chat. Okay, so I hope that everyone was able to do it. And we have, so let's now then move on to the next demo. And let's look at. But if you want more time, if you're still trying it, then you can tell me. I will can give you more time. Okay. So now let's look at the next demo. So far we have looked at how to use GDB. So now we will look at the buffer overflow vulnerability. And we were saying that if we overwrite the buffer beyond its, like not overwrite, if we write in the buffer beyond its capacity, then as you have like just seen the layout of the uh, memory on the stack, and if you overwrite it, then you can sorry, if you write beyond the buffers bound, then you can overwrite the values which are stored in the stack, like the EBP or the return address, etc. So here we have this very simple program buffer.c, which has the main function. The main function is taking arguments from the user. I mean, from the command line, it is taking the arguments, and the command line argument is then passed to this function copy buff. The buff function here is taking as input string, okay, characters string, and then it is going to create a buffer of size 50 bytes, and then it is using the str copy function from the string library from the libc, like libc from the it is going to use this library function call to copy the content of the uh, this string str into the buffer. And as we have already seen, that the str copy function actually is a vulnerable function here. The vulnerability here is existing because of use of this str copy, because the str copy function does not do any bounds check. So it's not checking what is the size of the buffer, what is the size of the string, how many bytes are being copied. It will just copy starting from the address pointed to by str until it's like until it encounters a null character. So it will just copy. Then the copy buff function, when it will return, it will come back here, and then you have this print statement done. The done way. Now let's compile this. And for that, for compiling it, we have the make file. The make file is just the script of commands that you can compile the function and sorry, compile the program. So here I have specified the flags that we were using here and the executable that is to be created, and then the GCC command is here with the flags. And then to compile, we can use the make command, and then if you want to remove any executable files, then we can use the make clean. So let's run make, and then this command is actually executed. It's the same command as before. And after this, we have successfully created buffer binary. And then if we will run the buffer binary, now here we will also have to give it some argument. So if we give some argument, say AAA, then the program runs correctly. I mean, there is no error. The program is printing done, so it executed normally and exited. So without any errors. But if you give it a arbitrarily long, say, input, so you can give any values you want. And but if you give it very long value, and if you run it, then you will get the segmentation fault that we were talking about, right? So now let us look at this from with the GDB, that what is happening. I mean, of course, we have looked at it before, but now let's look at with GDB exactly what's happening. So we are going to first list this program. Okay. Now we are going to, like, this is the program that we have. Now we are going to set the breakpoints here. So let us set the first breakpoint here on, say, the copy buff. Okay. Call to the copy buff. So we have set a breakpoint here. After that, we are going to run this program with a long input. So we have run this program, we have given this input, and then the program is running, and then we have set a breakpoint at line number 10. So the program will stop executing here. So now let's look at what and where are we. So we are currently here somewhere. Okay. And the copy buff here in the copy buff function, we are actually passing the argument that we have read from this command line. But we have some additional instructions here, which are, I think, related to, they could be EAX is there, move EAX. So actually they're computing the value of this. So computing the starting address, moving the start address of this string that you have passed from the command line. So this code is actually moving that address of that you have passed, address of this argument that you have passed from the command line into the EAX. And then so here you are pushing that argument that you're passing. It is basically just the address of the string in memory, and then you are making the call to the copy buff function. I mean, this is the relevant code to that we are looking at right now. And then, so that means let's first so since we are going to, so let's go here, inspect this. For that, we can actually say we want to execute 4 instructions. So we can say SI4 and then disassemble. So there we are now here on the push EAX. Okay, and then we have the call to the copy buffer function. Now let's first start by looking at the content of the stack. So this is the current content of the stack. The stack pointer is on D2F4, and also let's look at the EBP. I think is not, it is plus. Hmm. I'm just trying to understand this bit. So let's see what EAX contains and what will be pushed onto the stack. So EAX contains this address, uh, which is FFFFT566. So it is the address. I think this is the address of the string that we has been passed as the argument to this main function. So then that is to be pushed here. So we will do that, run one instruction and see. So this is pushed here and we print X. Although I'm not very sure if this will work or not, but let's try. Not yes. Print. This is printing the content of EX. That is okay. But I wanted to see what's contained at here. Anyways, so we have pushed the address of that string here, and then we are going to call the function copy buff. Okay, so now let's execute further and see. So then here we are passing it a. Yeah, so that's right. So this is the actually the address of the string FFFD566, which has been pushed onto the stack. And that is passed as an argument to the copy buff function where a is repeating 94 times. So now if we disassemble it, then we will look at the copy buff functions. And again, of course, we have seen it before. The copy buff function here has the push EBP, move ESP to EBP, which is setting up the stack frame as we have seen before. And then here we have some more things like push EBX. And this is, I think, is used with for computing the, this is some other code which is used here even when you are so this is not this is pushing EBX and this is being used somewhere else. But what we have for the buffer, actually what we, when we were in the code, if we will see, Then we have this character buffer of size 50. Okay, so the size is 50 bytes, and for that 50 corresponding to this buffer creation, here you have this subtract 44 hexadecimal to ESP. This instruction is there, which is corresponding to the creating the character buffer on the stack. So this is how many bytes? This is like 16 times 4 plus 4. So this is 68 bytes. The compiler has allocated here 68 bytes for this buffer, like the character buffer. And after this, we have the core. So of course, this is again computing the PC, etc. And after that, on line number 28 here, we have the call to string copy. Okay. And in the string copy, we are going to pass the arguments. We are going to pass here the destination address and the address of the destination and the address of the your I mean the source. Okay, so let's look at so the let's look at the local. So locals in the locals variables, you have the buffer as your local variable. And this is the address of the buffer. Okay, so in your stack frame, your buffer is actually starting from FFFD to AE. Okay, so it will be starting. This is FC and item 2A. So this will be, this is going to be F. If this is FC, then this will be F8. Then this will be F4, F0. And then this is BE. This is AE. Mm, okay. I'm finding it a bit hard to work with these hexadecimal values. But this is your buffer, and the buffer A address is this. And then your string that you're trying to copy here, the string address is this FFFD 566. Yeah. Now you are currently in the start of the copy buff function, and let's move the instructions, and then let's go to till the call instruction. Okay, so we are going to, okay, I think this was not even running. Maybe I should then check. First, let me just put a break here on the call instruction. So we have put a break here on the call instruction. Uh, yeah, so if we have put break, then let's continue. And so we are now, we are over here, the call to string copy. And then let's look at first the register values. So these are the register values F D290, D2E8. This is the ESP EBP. And this is your instruction pointer, which is pointing to the instruction here, 4846F. Okay. This is your local buffer, and this is what it is saying that currently your buffer contains. Okay, so currently you have actually not copied anything into your buffer. So this is what your buffer contains. It's just some garbage value into the buffer initially. And this is your address of the buffer. Now you, when you are going to make this call instruction to the string copy, then it is going to copy the content of str to buffer. Now before that, let's look at the content of the stack. So this is how your stack looks right now. Your stack is pointer is currently here. Okay, and so this is these are the two arguments to the actually to the copy function. Right, this is ffd 566 is the address of your it is the address of your string that you want to copy, and FFFD2AE is the address of the buffer. And actually, earlier when I was trying to find the buffer, I was not able to find it above because at that time I had not actually run those instructions. So that stack was not even created for that. Now the stack is created, and now if you will see that the address is D2AE. So D2AE means this is A0, this is will be A4, A like it will be A4, A8, and somewhere here it is D2AE. Okay, so your stack, sorry, you're not your stack, like you basically your this buffer is starting here. Okay, and your buffer is of 68 bytes. Okay, so your buffer is starting here, and the buffer is of 68 bytes. And your these are the arguments to the function strcopy. So if you have any question or if this was confusing, because for a while I was confused myself, and if you want me to explain it again, then I can do that. So, but there is no question on the chat. So let's. So currently we are here. The instruction pointer is on the call instruction. This is the content of the stack. The last two values here are the arguments to the strcopy function. Okay. And then we are going to run, say, let's again add a breakpoint. So by using B, we were like able to print like where our breakpoint set. So that will print. And so let us add a breakpoint at the next instruction after the call. Okay, and that's okay. But I again just a quick question. So when you will call this function strcopy, what will be the values of EIP? What will be the value of EIP? And what will be the value of return address? Yeah, so that is right. The current and the value of EIP will be changed to this value because this is the address of the strcopy function, and the return address which will be pushed onto the stack is this value 8048474. Okay, and so we have added a breakpoint on this instruction where we are going to return after finishing the str copy function. So then, but let's just run one more instruction. So when we run one more instruction, at that time, we have now entered into the str copy function. So let's just assemble and see. So yeah, we have entered into the str copy function, which is like jumping to somewhere else. And here is our instruction pointer. And then let's look at the content of the stack once. So if you will look at the content of the stack, then uh, as you were saying that it has the address of the next instruction here, 80484744, and these were the arguments that were pushed earlier. Right. So next, let's just continue the execution. And if we continue the execution, then we have already added a breakpoint at the return instruction, right? So it's now going to stop there. So now we have finished the str copy function and we have come back here. So currently we are still in the copy buff function, and this str copy function, what has it done? It has copied the content of the string that you have provided as input to the buffer. Like it has done this. Now what will happen? Now after this, you're going to return from this function, right? And then you are so first let's look at the content of the stack. How has it been modified? So as we were saying that your stack was starting somewhere here, right? Sorry, not the stack. Your buffer was starting somewhere here, and you have given like 96 bytes or something as input, and those bytes were like all A's. So the ASCII value of the capital A, which is 41, has been written here all or on the entire stack, like all like here. The entire stack up to here has been rewritten with 41 value. So the return address which you had added to the main function, which was added before, actually that is now no longer present. So what will happen if we will execute these next instruction? Let's execute them one by one. So here it is adding 16 bytes to ESP. So it is basically going to pop these values. Then there is a no op. Then it is actually computing something in EBX, and which also I am going to skip for now. And then we are going to focus on that next. So let's now we are here. Let's execute the next two instructions. Let's look at the stack. So this is how your stack is looking right now. Okay. And after this, it is EPP -4 or something is being pushed back to EPX. Then there is leave. Now the leave, sorry, the disassemble. Currently we are here on the leave. Okay, so now let's execute the leave and now look at the stack. So we have executed the leave function, so it would have removed the buffer like and the local variables. And then the leave is also going to do what? It is going to reset the value of EBP to what it's present on the stack. Okay, so info registers. So maybe you can answer now. What will be the value of register EBP now? So you have overwritten the stack. Now when you execute the leave instruction, so it will try to restore the value of EBP from the stack. So what will be the value of the EBP? Yes, so the value of EBP will be like something like 0x41414141 4 bytes, right? So if you check here, the value of EBP is all 41414141. And currently we are on the ret instruction. So then let's execute the ret instruction. So when we execute the ret instruction, then what happens? When we are executing the ret instruction, then it is going to read the 0x41414141 as a address from the return address from the stack. Okay. And then because this address is actually not a valid address, uh, and it's an invalid address, so that's why we get a segmentation fault, because we are trying to execute from somewhere which does not exist. So that's how you got a segmentation fault. And if some step was not clear, then you can ask me. And that is how you were that's like the buffer overflow, how the buffer overflow happens, and how it corrupts the EBP and the return address or something, return address, EBP, and the other parameters which are stored in the stack. And then when you try to return, then it will cause a segmentation fault. Now, if there are any questions, then please put them in the chat box. And now, what we are going to do is so if there are any question, then you can put them on the chat box. So now you can you try to like do this buffer overflow? Can you try to run the files that I've given you and just try to do this? And then maybe, like currently what we did was that we gave it some input, right? A something. With this input, it was running. So can you look at this if you're able to run it and then tell me that how many bytes you write? Like currently, if I write here, say buffer with 3, if I'm giving it 3 bytes, of course it's running correctly. In the last, when we look with GDB, we gave it 96 byte and then it was crashing. So if you will run it with the GDB, and maybe you can look at the assembly code, or you can look at the stack so you can do it many ways. You can look at the stack layout, or you can try it with different input string lengths. So the question is, what is the minimum size of this string that will cause it to crash, that will cause the segmentation fault. So that's what we have to find out. Yeah, the recordings, yeah, it's been recorded and the recording will be there in the chat. If you are not able to download it, then let me know. I will download and put it on, say, YouTube or somewhere. But otherwise, it's, I think, hopefully accessible to everybody. Yeah, so it will depend on the binary, right? So you can look at the binary or you can look at the stack. So the question is, like what I'm saying is, can you try to run this with GDB, or you can maybe just run this program and give it different length of inputs and try to find out like what will be the size of what is the length of this string, minimum length of this string, which will cause the program to crash. And before you answer that, maybe you can think about like, when will the program crash? Yes, that is absolutely right. So it depends on the like what the compiler has generated in the instructions. It has allocated here 68 bytes. So 68 bytes is allocated for buffer, and there could be other bytes or something. So the question is, of course, it is depending, but you can run it with GDB and try to find like the minimum length. Say for you try to run this program in your machine and try to find what is the minimum length, because that is going to be useful when you are going to now create the payloads. So it's important for you to find out what is the minimum length. Now, why am I saying the minimum length here? So the question is, when, why is the program crashing here? So the question that I'm asking, let me just write the question here. When will the program crash? Why is the program crashing here with segmentation fault? We just looked with the GDP right now, and I just talked about it also. So can you tell me why was it crashing? Yes, the address is not found. What address? What? This is the address for what? Which address is not being found? Which address is not found? You're right that it was looking for something, right? We were looking at the demo. We uh, have filled the entire buffer with 0x41414141, but then we were got a segmentation fault. Yeah. So it's related to the return address. So see, when we executed the leave instruction, there was no segmentation fault. Okay. So what is the leave instruction doing? It is restoring the EBP value to the previous EBP value. Okay. So leave instruction is restoring value of the frame pointer EBP. And I am not sure if it's no longer available. GDP. Yes. It's okay. So what I'm doing here, I'm again showing you that where exactly was it crashing? Because the question is, why is it crashing? So here we are again running the program, and with some this value, this basically string, and the string is, so it's now breaking here. It's saying cannot access memory at this address. But I think I should have set the breakpoint above itself. Oh, so it's actually not crashed here. Of course, it's TR is we have run this program. This is the argument, and then we are currently here. Okay, this is how your stack frame is looking. Okay, not the stack frame. I mean, this is how your stack is looking right now, and you're currently here. This is your EIP, and you're currently in the copy buffer function. Okay, and now let me put a breakpoint here. And then the continued execution. So if the program is still continuing the execution, even though the stack has been like rewritten over, there is a stack overflow here, buffer overflow here. So now we are in the leave instruction. Okay, and currently we are on the leave instruction. The leave instruction will be executed next. And this is how your stack frame is right now. No, this was before. So let me just actually G. Yeah. So this is basically same only. This is your basically this is your stack content. Okay. And currently you're on the leave. So what does the leave is going to do? The leave instruction is going to change the value of the EBP, which is the frame pointer, and set it to equal to the previous frame pointer, right? And so for that, and I think, which I keep forgetting again. I think it is also going to uh, change your ESP. So let's just print the value of the registers. Correct. So this is the current value of these two registers, ESP and EBP. Okay. So this is your 280. This is like the top of the stack ESP, and 2C8. 2C8. So it is 0. This is 4. This is 2C8. This is your stack frame. So your stack frame for the this function. So this is the current stack point, like stack frame pointer. So it's starting somewhere here. Yeah. Now, when you are going to run this leave instruction, it is going to copy. So this is where the stack frame is starting. Okay. And before that, this is your EBP, previous EBP, but it has been rewritten because you have overflowed the buffer. So what will happen next is that it is going to uh, change the value, like the value of now your new value of ESP becomes D2CC, somewhere D2CC. So it's 048 and here. So it's has come all the way here. And all of those values have been like removed from the stack basically. And your stack pointer, sorry, your EBP has been reset to 414141, which is uh, basically earlier your stack previous stack frame was stored there, and now it has picked up this value. Now, but what does this show? That you were able to run the leave instruction, the EBP value was corrupted, but still your program did not crash, right? But now if you will run this one more instruction, which is the return instruction, then the return instruction is going to say like crash the program. Why? Because the return address that it is going to pick from the stack, that is 414141, that is an invalid address. So it is going to cause a segmentation fault. So when I'm saying that what is the minimum length of the string which will not cause your program to crash, or which will cause your program to crash. So that will be, you can write starting from the buffer start address till the till right before the return address location. And if you write in this range, then you will not crash the program. Now, this is also important because this will tell you exactly where your return address is located. So if you write, say, 70 bytes, no, let's say if you write 68 bytes, because your buffer is, say, 68, but if you write 68 bytes, then if it doesn't crash, that means it's safe. Then if you write, say, 72 bytes and it still not crashes, then it's safe. If you write, say, 26 byte and it crashes, that means that your return address was located from byte 72 to 76. Okay. So now, do you have question about that? So now to find out this, like what will be the length? Of course, we can go back and look at the stack. And then because we have just seen that 68 bytes are allocated for the buffer, so we can do that, but we can also here say generate a payload. So initial, so you know that your buffer is of 68 bytes, right? So what it is going to do is that it is going to generate a string of length 68 bytes, which should be a safe sequence, right? Because the buffer size that you have allocated is this much only. So you will, it's still causing segmentation fault. That's a bit your Mm. Okay, yeah, sorry. So, okay, so why is this happening here is actually when we were running, I think I again keep forgetting this every time because what is happening that on my system, I have not disabled ASLR. So like currently whatever I'm running on, and so this is going to be randomized. And so what when we are working with GDB, actually the GDB is going to provide us this a debugging environment, and it is not it has like say disabled ASLR or something. So then every time it is going to place your like look have the stack layout same. So we can try this in the GDB, but it is not going to work here actually. So I will have to do it in the GDB only. Didn't put the same by name. Okay, so now we are here. Now we are going to copy that and run, but still getting that. Okay, then let's look at the binary again. So we have this. So let's do add a breakpoint at line number 6 here. Okay, and so then we are going to run the program and okay, that is actually before only. So we have to start the program again and second. Yeah, so we are starting the program again. We have added a breakpoint here on string copy. Okay, so now let's look at the disassembly. Oh, I thought it's 68 bytes been allocated. For is yeah, 68 bytes have been allocated, but probably from where it's starting that is different. So then we will have to okay, let's look at the content of the stack and see where it's located. Mm, let's see. So this I think is the return address of the main function. This is the frame pointer. I'm this looks like the return address of the main function. This is the previous frame pointer, and after that, it's going to allocate this many bytes. Mm, ES. So let's print. So this is the start address of this buffer T2CE. This is C0 and C4. Uh, C8, and then this will be somewhere here. The buffer is starting here. 64. But this doesn't look like 68 bytes to me. Actually, hmm, this is push EBX. But this is 16. This should be the start address. Is should okay. No. Okay, so it is possible. I think what I am understanding right now is that it's possible that the this is what has been allocated here. Basically, 68 bytes are allocated here by doing this subtract. But the start address of your buffer is actually not here. The start address is somewhere here. And that's why it's like not 68 bytes. Because as you can see, I mean, that's like subtract, this is 68 from ESP. So the 68 bytes were subtracted. This is your EBP, which was pushed. This is your EBX, which is pushed here. And after that, there is subtract. So this is subtracted. And this is, of course, this so far, this is how you have modified the ESP. Right. And then your buffer address here is actually starting somewhere here. So it's not entirely going to write from here, 68. It's going to write somewhere from here. And we can verify this, of course, by doing a step-by-step execution. Let's try that. And so I've added what I can say, a breakpoint here so that I will be executing till here. So we will execute till here. So now we are here. We are called to the copy path function. Now let's add a breakpoint to the next instruction. Okay, so we have added a breakpoint here, and now we will let the call to execute. So call is say executed. What's happening? Let's look at the content of the ESP. T2C00, T2C00. Yeah, so you were here. So it has not started actually writing from right from here, which we were like, which I was expecting. It started writing from CE, and then it is writing. And when, even though I've given only 68 bytes, thinking the buffer is 68 bytes long, it's actually uh, here has overwritten the return address, which was here in 3009. Yeah, so that has been overwritten. So, so then, so I hope that makes sense. Yeah, so how to find the crash limit of the program? What I was saying is that we can generate these when we were talking earlier. Also, we were sort of talking about something like first testing, right? We are going to give these random size inputs to the program. Like here, actually, I tried to give 68 because I thought that the buffer is of size 68, so it will be safe. But as we just saw that the buffer 68 bytes has been allocated by used by the instruction, but the buffer is actually starting from somewhere else here. And so when we can find the crash limit of the program by giving it sizes like input of varying sizes. Okay, we can give it like input of varying sizes. Okay, so here you have tested it. So let's see. I will just quit this. Come back here. Let's try 55. For me, I think even 55 is giving a crash. So let's me try even lesser values. How is it even possible? The buffer is of size 50. The buffer is actually of size 50, right? I am not very sure now. Yeah, the buffer is of size 50. Yeah, so I just gave 50, so it's running fine. So now 55, it was giving error. So let me try to make this 54. Even the 55 should also not give a segment. Okay, I am again making a mistake of doing it in this side. Uh, sorry about that. I am have to like do it in the GDP. I should do it GDP 54. So this is 54 bytes, and let's see, try with the GDP. So this was 54 bytes. So it was running correctly. Now let's try with other values. Let's make it 60. So now we are getting a segmentation fault with 60. Hmm. Although the address is 54, 50. This is actually This is not the address which is we are adding here. So only with value up to value 54, we are getting it's actually okay. But beyond that value, we are actually getting segmentation fault. I mean, for this particular program here, we are the buffer size was 50, and here if we are writing uh, 54 bytes, then this is executing correctly. But beyond 54 bytes, it's actually giving a segmentation fault. So I think we would then need to inspect it a bit more to understand exactly what's happening, because I was not expecting this. Um, but I think I will look at that. But so far, what we have discussed, and I think what we have seen here is that uh, what like say we've seen how the stack will change when you write these say a very long. If you give a very long input to the program, then it will overwrite these values which are stored on the stack like EBP and return addresses, and then corrupting them. And so then later, if your program is trying to access some address, and then at that time, if it doesn't find, if that address is invalid, then it will lead to a segmentation fault. And here with this exercise, basically we were like trying to find out that what is the safe length, like till how long can we write without corrupting, because corruption will happen, let's say, when we rewrite the return address. Or so at that time, like if we rewrite the return address with something garbage, that time it's causing a segmentation fault. But if we rewrite the return address with some valid address, like address inside the stack only, yeah, address of some instruction in your program, then it will not give a then it will not give a segmentation fault. Now this 414141 etc. It was giving a segmentation fault only because that is an invalid address. Yeah, so it is. So this is how. Yeah, so I hope that this was clear what we have looked at so far. Yeah, this was. I think I will have to then look at it, or you can also look at it again later, that exactly find out what is getting corrupted on the stack when you're writing beyond 54 bytes, which is causing this segmentation fault. You can think, like you can take it as an exercise and you can find it out, and then you can even let me know about this. And now I think we have okay, now we will take a short break till for 15 minutes. And in that time, if you have any question, you in that, of course, take a break. If you have any question, then you can stay and you can ask me something. And I then when we return back, then we are going to I will go show you this basically code, how you can create a shell payload. Like you can write code on the stack and then you can modify the return address to invoke that. That we will look at when we come back. And after that, we will look at the defense stack canary and other defenses, how we can enable and disable them. And I think with that, we will then wrap up the for today. I mean, no, wrap up in the sense that I think I will stop teaching, and then if you have any question, then you can ask those questions, and then we will start with the rest of the exploits tomorrow. If you have any questions, then please put them in the chat box, and let's take a break till 4:50. Yeah, let's come back at 4:50. I'll stop the recording and I will start it again when I'm back.